Hello there, welcome to another episode of Science and Technology Q&A for kids and others. So I'm happy to try and answer kind of fact-based questions, but I'm also happy to answer questions along the lines of how would you think about this or that kind of problem? So let's see, I see a bunch of questions saved up here. There's one from Sobhan here saying, when we transfer an electric charge to a conducting sphere, does the charge cause some metal ion atoms to become ions? If they do not become ions, where do the electrons go? Okay, so let's talk about electric charge, metals, all those kinds of things. So first question is, what is electric charge? It's a property of particles like electrons and protons. And so far as we know, all electric charge comes in little quantized units. So an electron has -1 unit of electric charge, a proton has +1 unit of electric charge. The quarks that are inside things like protons, they have 1/3 of a unit of electric charge. The up quark has 2/3 of a unit, the down quark has -1/3 of a unit of electric charge. Quarks aren't things that get separated. If you try and pull two quarks apart, they'll form this kind of flux tube of gluons in between them, and the harder you pull, the more difficult it will be to pull them further apart. So they get sort of permanently confined inside protons. So as far as we're concerned, the only electric charges that we see as free charges out there in the universe are made from things like electrons and protons. There are other kinds of particles that also have charges, but they're always in units of the electron charge. You might ask, why is that the case? Nobody knows. I think we have some ideas in our theory of physics. There are some ideas that have been floating around for nearly 100 years, actually, about why charges might be quantized. Maybe I'll talk about those separately. But anyway, the basic point is electric charge is sort of counting the number of electrons, the number of protons, and each one contributes either -1 or +1 electric charge. Okay, so then there's the question of, when you have an ordinary atom is a combination, has protons and neutrons in its nucleus and has electrons outside. And an ordinary atom has an equal number of protons and electrons in it. And so it has plus some number of units of electric charge associated with protons, minus some units of electric charge associated with the electrons, and the whole atom has zero charge. That's its sort of usual state. You just have a separated atom of something hanging out there. It'll have zero electric charge. And in general, the electric charge of the nucleus is just the atomic number of the element. So, I don't know, helium, for example, would be 2. And so it has 2 protons plus 2 electric charge. And an ordinary helium atom will just be a +2 electric charge and a -2 electric charge for the electrons. Okay, so when atoms get put in close proximity, one atom might pull the electrons away from another atom. And so if you looked just right around the atom, it would not have the number of electrons that you would sort of expect based on equaling the number of protons that it has in the nucleus. So for example, whenever you have ionic materials like salt, sodium chloride as an example, you'll have something where there is it's often written as Na plus Cl minus, and that means that the sodium atom has had its electron pulled away, or one of its electrons pulled away. The chlorine has had an electron pulled closer to it, and that's part of the mechanism that pulls those atoms close to each other, so to speak. So okay, so in ordinary materials, the electrons can be just pulled a little bit away from just being sort of in their natural habitat right inside a single atom. They get sort of pulled away from that atom, but they're still kept localized close to the atoms that they sort of were associated with. Okay, so the thing that happens in metals is that there are electrons that are kind of shared between many atoms. What happens is that there are electrons, you can think of them as essentially close to the nucleus that are very tightly bound. Electric forces bind them very close to the nucleus. They don't get to go anywhere. But then there are electrons that are sort of further away from the nucleus. And the way the material can be set up is such that there eventually are electrons which kind of freely float from being in the region of influence of one atom to another. In the terms of quantum mechanics, it's called the conduction band. It's where the electrons that are close to the nucleus are held in with lots of energy. As you get sort of further away, you eventually get to electrons where they kind of can equally float between different atoms in the material. So what leads to electrical conductivity in something like a metal is that there are electrons that are not tightly bound to single atoms, but are sort of freely floating in this conduction band. So what then happens is that if you put an electric field across that metal, the electrons will be pulled in the electric field and will just sort of freely flow in one direction or another. That electric field is what you get when you apply a voltage to the piece of metal, and that voltage is you're basically that is creating an electric field. An electric field is something where there's kind of a kind of defines a flow. Like you could have if you had something like water, you would have something where there was an actual flow of water from here to there. In the case of electric field, it's more abstract than that. It's a feature of the electromagnetic field, which is not something you can just sort of pick up like you can a material, but it has the same characteristic that it can sort of flow from one side to another, and that defines the electric field. And the electric field is what will move electrons around. And when the electrons are sort of in this conduction band, they're kind of freely able to move from one part of a piece of metal to another. So it's not the case that basically these are shared electrons between lots and lots of atoms. And it's not that one atom gets its electrons pulled away from it. It's that that atom is sharing electrons with all the other atoms. So just to explain, you mentioned ions. So normally an atom has equal number of protons in the nucleus and electrons around it when it's sort of an isolated atom. But if you, for example, heat it up, if you kind of kick it around enough, then eventually it will become ionized, which means that electrons will be stripped away, and you'll have something which has which actually has a net electric charge, where there's and that's what happens in for example, when you have fire or you have a plasma, it's a bunch of ionized atoms where electrons have been stripped away. But that's a much more violent thing than what's happening with the sort of sharing of electrons in something like a metal. What happens in metals is you have this electric field and it's pushing electrons from through the metal. If the electrons have a certain resistance to motion, and that happens mostly because the electrons are hitting pieces of the atoms in the material. They're not just able to go without resistance, so to speak. They're running into one thing, then running into another thing. They keep on getting sort of moved by this electric field, and the amount of resistance. That's when you have a electric resistance or you have a resistor or something, it has a certain, it's setting things up so that the electrons have a certain resistance to being moved through the material. So sort of famous result of basic electrical theory is Ohm's law, voltage equals current times resistance, which is to say if you want to have if you have to the voltage, you need to push the electrons with a certain force effectively to get a certain number of them to flow. That's what the current is specifying for a given resistance to the motion of the electrons. So anyway, so in something like a metal, the electrons will be sort of fairly free to move around, not completely free to move around because there is some resistivity in ordinary metals. In superconductors, certain materials at very low temperatures get to the point where electrons can flow completely freely, where there's no resistance to their motion. So that the resistivity of the material is zero, and you can have all kinds of cool things, like you can have an electric current that's circulating in a superconductor, and it'll keep circulating for months without dying down. In an ordinary metal at room temperature, let's say, that doesn't work that way. There's sort of too many imperfections for the electrons to hit, and so there's resistance to that motion. So anyway, uh, that's that's how that more or less works in the when you I think the question was if you when if you take an electric charge, so you can get electric charge sort of in one place. For example, if you rub something, you get static electricity. That happens because effectively you're removing electrons by that pure act of rubbing. You're you're moving electrons around, and you're ending up with something where there's a net electric charge in that place in the material. And if that electric charge, if the material is not a conductor, not like the case of metal where the electrons can sort of flow freely, but it's what's called a dielectric, where the electrons are kind of stuck within their atoms, then if you get it to the place where there are too few or too many electrons somewhere, the electric charge will just stay there. And if you then sort of connect that to a metal, for example, the electrons that were in the in that sort of lump of static electricity will indeed get transferred to the metal, and and then we'll end up. So yeah, this is getting a little tricky because you have to talk about. I mean, the main answer to the question is that the electrons in a metal don't are just shared between lots of atoms, and so there isn't it's not the same kind of thing as sort of tearing electrons away from their atoms to make things like ions. Um, let's see. My gosh, there are questions here. Dougie is commenting, in the recent fires in Los Angeles, I've seen buildings burnt, but plants and trees next to them just fine. Is there a physical or chemical reason why the plants are fine, the buildings not? My guess is the number one issue there is that the plants, if they're live plants, have water in them, whereas a building that is made of wood, for example, it doesn't have that kind of moisture in it, and so there's a it that it's more liable to catch fire. Now, it is an interesting question. What um, what makes materials combust? Typical materials, there'll be a certain temperature at which they will spontaneously start burning. If they're in air, things will start to oxidize. There'll be a chemical reaction that can happen where oxygen will combine with let's say carbon or something in the material, and the thing will start hydrogen in the material, and the thing will start to burn. And that happens. Usually what happens is there's a certain potential barrier associated with the uh, um, the kind of oxygen getting in to combine with those other atoms. And if the temperature is high enough, there'll come a moment where the oxygen can kind of get over that potential barrier and start to combine with those things. And the result will be that in the end, once it's combined, the energy is lower. And so once the material has started burning, that will be a thing that tends to keep happening. Now, I don't know what uh, different materials have different um, that works differently. And for example, for water, where um, I think probably because of the chemical forces being large between the hydrogen and the oxygen and so on, not sure if that's the best way to think about it. Um, it's, when there's water, this doesn't happen. And it's and so if you have something which has water in it, that's a good thing. That's why, you hose down buildings and things to uh, that helps. And I think that would be my guess is if it's dry and if it's a living plant, it's not dry, and otherwise it can be. And I think it's a quite different question whether structures, brick, stone, and so on structures, those only start to burn and so on at much higher temperatures than things like wood, I think. Um, the um, let's see. A question from Tony here. Do photons collide? And with uh, if you have a stream of photons, like you have a very bright laser that has tons of photons going in some direction, then you shine another laser in the opposite direction, what will happen, so to speak? Well, okay, it's kind of tricky. The first question is if you have so in a laser, for example, there are you can think of a laser beam as containing a huge number of photons, but those photons are very correlated with each other. It's not the case that it's like, oh, first one photon hit you, then another one, then another one. It's a more complicated thing where the photons sort of together act like more like a wave than they act like individual boom, a photon hit, another photon hit, another photon hit, and so on. If you have photons of things like X-rays or gamma rays, they're much more like one photon at a time. It's like, okay, that gamma ray photon just hit me, then another one's going to hit me, then another one's going to hit me. So it's a little easier to talk about what happens with photons that are the higher energy photons of things like gamma rays than it is with photons of light. But let's talk about those. Let's say you have two high energy photons that are aiming right at each other. They hit. What happens? Well, there is in fact a process. It's usually called light by light scattering, where two photons can interact. It's a tricky thing where it's a feature of quantum field theory, quantum electrodynamics, that lets that happen. So, okay, first thing to say is generally when you shine two lasers, one goes in one direction, one goes in the other direction, the photons effectively just pass through each other. They have certain other effects, which we'll talk about in a minute, to do with the wave nature of light. But as far as the individual kind of particle-like photons, they don't interact. The Now, when I say they pass through each other, that's kind of a weird thing to say because photons as particles seem to have zero size. I say seem to have zero size because in our model of physics, they probably don't have zero size in the end. In traditional physics, that they've usually been sort of assumed to have zero size, and there's no at least a sort of a free photon, not kind of interacting with anything, seems to have zero size. So, okay, how does light by light scattering work? What happens is the following. So, I mean, I'll say it quickly and then I can explain what I mean. You form a virtual electron-positron pair. Actually, there's this kind of space-time diagram, Feynman diagram, that you can make of light by light scattering. It's a tricky thing. You've got two photons coming in. Those two photons both well, the diagram is kind of a box. You have two photons coming in. You make you each photon kind of makes a virtual electron-positron pair. Those interact. they reannihilate again, you get two more photons again. So let me try and explain what on earth is going on there. So first thing to say is in quantum field theory, there are particles like electrons and photons, and they have a certain normal set of characteristics. They have a certain mass. Photon has zero mass, so far as we can tell. Electron has a mass of about 1,800 times less than a proton. They just have definite characteristics. However, according to quantum field theory, it is the case that if you have an electron which is produced at some moment in time and then destroyed at some later moment in time, if those moments of time are close enough together, the electron can kind of not be the way an ordinary electron is for that very short amount of time. What can happen is, like, for example, for a photon, normally it has zero mass, but a so-called virtual photon that is produced and then destroyed, a trillionth of a second later, a photon that lives only for a trillionth of a second can behave as if it has a mass that's not zero. In fact, something that lives a trillionth of a second could behave as if it has a mass as big as the mass of a proton. It's a feature of quantum mechanics and quantum field theory associated with, you can think about it associated with the uncertainty principle, that if you have a short enough time interval that something exists, then its characteristics, for example, its mass, can be substantially different from what they were if it's just free and existing forever. So what can happen is there are these virtual particles that exist for a short amount of time. And for example, a photon can turn into a virtual electron-positron pair. The positron is the antiparticle for the electron. And when you combine an electron and an anti-electron, that can turn into just pure photons. Now, normally, a photon that's just going along, it has zero mass. How could it possibly turn into an electron-positron pair, given that the electron has a mass of, well, it's half an MeV, half a million electron volts, half 1/1800th of the mass of a proton, for example. How could a zero mass photon turn into electrons and positrons? Well, the answer is it can't turn into real electrons and positrons, but it can turn into a virtual electron-positron pair, where that virtual electron-positron pair effectively has zero mass, and it can do that if it exists only for a very short time. So what's essentially happening is that the photon is turning into an electron-positron pair. One photon is turning into an electron-positron pair, but as soon as you have an electron, or a positron for that matter, a photon will interact with that electron. So that other photon that you had that you were trying to make interact, that other photon can interact with the virtual electron, for example, produced from the first photon. So what happens, you can think of it as a photon is, for a brief moment, it turns into an electron-positron pair, then that other photon comes by and it doesn't see just a photon there, it sees an electron-positron pair. So it says, okay, that's a thing with electric charge. I interact with things with electric charge. It will have an interaction with that. And so for the way that light by light scattering works is photon briefly turns into electron-positron pair. That electron-positron pair can interact with the other photon and produce an effect where it looks as if the two photons are interacting with each other. The effect is very small, and the effect is it essentially as the energy of the photons. If the energy of the photons is comparable to the mass of an electron, that will make, with sort of high energy gamma rays and things, that makes the probability of light by light scattering somewhat larger. It's still, I think it goes like the energy to the 8th power, if I remember correctly, is the rate of that. So very, very, very high energy photons will have that that kind of effect. One place, now that I remember it, that will let's see. No, that probably isn't such an important effect. The very high energy cosmic rays can scatter from the photons in the cosmic microwave background. And most cosmic rays are protons, so that's kind of unremarkable. But you can also have scattering of high energy photons from as a result of this effect. But anyway, so that's this phenomenon of light by light scattering. It's a small effect. It has been observed experimentally, but if you just have two laser beams interacting with each other, what happens? This effect is completely negligible there. What can happen is that the sort of coherent effect of all those photons organized, they sort of are organized into this, into kind of a wave in which well, there's electric field and magnetic field. That's what kind of determines, light is this thing that has electric fields and magnetic fields that's what light, you can think of light not in terms of photons, but in terms of the kind of these oscillating electric and magnetic fields. And when you have sort of a laser which you could either think of as tons of photons, or you can think of it as all those photons are acting together, and you can think of them better in terms of this electromagnetic wave. When you have that electromagnetic wave, it can be the case that two different electromagnetic waves interfere with each other. Essentially, one of them has an electric field that at this position in space at this moment in time is plus whatever it is. The other one might have minus whatever it is, electric field. And so the net electric field there might be zero. You might have destructive interference of these two laser beams, for example. And that's something which is specific to lasers. If you have light that comes from, I don't know, an incandescent bulb or something like this, it's a big cascade of sort of photons that don't really correlate with each other. Lasers have this feature that they're producing coherent light, where all the photons are kind of acting together, and you can think of them as corresponding to these definite electromagnetic waves and so on. In the case of sort of light that's produced just from heat in an incandescent bulb or something like this, every photon is kind of acting on its own, and you don't have this sort of coherent effect of thinking about sort of a whole electric field associated with one laser beam compared to the electric field associated with the other one. Boy, I think these should be, well, anyway, these are questions of yeah, it's kind of tricky because some of what I'm telling you is kind of high school level physics, and some of it is fancy particle physics that you might learn in graduate school in physics. So it's kind of a funny thing because there are these very different levels of discussion that one has to have. Let's see. Okay, there's a question here from the Rouliad, good handle. Question about antimatter. How does one contain antimatter? Well, so antimatter is, so things like electrons, there are antimatter versions of electrons, anti-electrons, positrons. What's the difference between matter and antimatter? The difference is the electric charge and other kinds of charges of antimatter is always the reverse of the charges of matter. So for an electron, the electron has electric charge minus 1 unit. A positron, the anti-electron, has electric charge plus 1 unit. And that's really the only difference. The mass of an electron is the same as the mass of a positron. They both have positive mass, but the electric charge is reversed. There are some other kinds of charges that one can talk about, thing called strangeness, charm, other kinds of things that work a bit like electric charge, and those also get reversed for antiparticles. But so things like protons, there are antiprotons, antineutrons. Even though there's no electric charge for a neutron, there are other kinds of charges for a neutron, and they get reversed when you have an antineutron. For a photon, photons are their own antiparticle. An antiphoton is the same as a photon. That's going to be important when we talk about how you contain antimatter. But so photons are their own antiparticle. There's no antiphotons. It's all just photons. Most other particles, there are anti-versions of them. In fact, there are very few particles that are their own antiparticles. Higgs particles are another example of a particle that's its own antiparticle. But mostly, most particles, there is a distinct kind of thing that is its antiparticle. So how do you make, so for example, how do you make antimatter? Mostly, you make antimatter by making it along with matter. So I was actually just talking about photons, where a photon can turn into a virtual electron-positron pair. You can make that by colliding that photon with something. You can make that into actual electron-positron pairs, and so you'll end up with a positron along with an electron being produced from that process. There's actually one other case where you make antimatter fairly easily, which is certain radioactive decays emit positrons, not electrons. The radioactive decay that comes in alpha decay, beta decay, gamma decay. Alpha decay is spitting out little helium-4 nuclei. It's kind of that's one form of radioactivity. Beta decay is spitting out either electrons, and usually that happens because you get an electron because a neutron in a nucleus is a little bit, neutrons on their own, okay, so protons on their own, so far as we know, are completely stable. If you just have a proton sitting there, it will sit there forever. We know its lifetime is more than 10 to the 32 years. So that's, incredibly much longer. That would be a trillion times longer than the lifetime of the universe, at least. So protons seem to be stable. Neutrons, on the other hand, if you can get a free neutron, then free neutrons last about 15 minutes, and then they decay. When neutrons are bound inside atomic nuclei, they don't have the opportunity to decay. They don't have the energy conservation doesn't work out so that they are allowed to decay. When they do decay, a free neutron decays into a proton, an electron, and an antineutrino. So a neutron has zero charge, a proton has charge +1, an electron has charge -1, and a neutrino has charge 0. So it works out, neutron charge 0 decays into a thing with +1 charge and a thing with -1 charge. That antineutrino is an extra little piece, because I mentioned there are charges other than just electric charge, and one kind of charge that there is a charge that's associated with electron number. And so you can't just produce an electron because that has an electron charge of 1 unit, and you've got to have something to compensate for that. And an anti-electron neutrino has an electron charge of -1 unit. And so that's the thing you produce along with an electron to sort of cancel out those charges. So a free neutron decays into proton, electron, antineutrino. Antineutrino is a particle of very close to zero mass that has very little interaction. Lowish energy neutrinos will pass all the way through the Earth without interacting. But in any case, so a free neutron decays that way, produces an electron, and if there's in a nucleus, if the neutrons aren't being held in enough, they can decay, and that leads to a kind of radioactivity. It's beta decay. Beta was actually the old-fashioned name for an electron is a beta particle, and so what's happening is the neutron is kind of loose and manages to decay and produces an electron, and then there'll be a proton left in the nucleus, but the electron will escape, and that will be a piece of radioactivity. So that's one case. Another case that can happen is there's sort of a proton that can convert into a neutron, emitting a positron. So the proton is sort of it has a +1 electric charge, and so that has to go somewhere. And a positron conveniently also has a +1 electric charge. So what will happen is you'll get conversion from a proton to a neutron, plus a positron plus a neutrino. And that sort of matches all those things. And so that's another source of positrons is that kind of beta plus decay, it's called. So, do I know a beta emitter, a beta plus emitter? Let's see, I think, yeah, tritium is a beta plus. No, it's a beta minus emitter. I forget. I have to look it up on a table of isotopes. But in any case, the thing that so those are two sources of antimatter. One is radioactivity, makes some positrons. The other, you can make any kind of antiparticle by essentially converting things like photons into particle-antiparticle pairs. By the way, in the very early universe, it was just full of particle-antiparticle pairs. In the very, very early universe, there were probably equal numbers of particles and antiparticles. One of the mysteries in our universe is that everything is matter. There's no antimatter. There are no, when I was a kid, for example, it was still a possibility that there might be anti-galaxies made of antimatter. In fact, I even studied that a bit. And it could have been the case that there are, our galaxy is made of matter. Okay, this galaxy over there is made of antimatter, and there might even be some force that would keep those galaxies apart. But that's not how it is. How it actually is that every galaxy is made of matter. There isn't any sort of antimatter just hanging out in the universe. And that's a strange thing because in the very, very early universe, we pretty much know there was an equal amount of matter and antimatter. In fact, back in the 1970s, I worked on the question of how one ended up with a small excess of matter over antimatter. So when the matter and antimatter kind of annihilate, most of the matter and antimatter annihilates, but about 1 part in 100 million of that matter, there's an imbalance between matter and antimatter. And so the end result is that we end up with a universe that has matter, but not antimatter in it. But in any case, in today's universe, the only way you get antimatter in any things like antiprotons is with a particle accelerator, where you're putting in lots of energy, and you're converting, let's say, high energy photons into proton-antiproton pairs, and then you're having to harvest the antiprotons. Now, it's a little difficult to harvest the antiprotons because when you produce them, they're usually going pretty high speed because you just produce them from a bunch of energy, and that will tend to make the antiproton go. It will have a bunch of energy. You can by playing various tricks, you can reduce the amount of energy it will typically have, but roughly it will end up having a certain amount of energy going in a certain direction. You have to kind of capture it, and you do that with magnetic fields. And the point is, I mentioned that photons are their own antiparticle. That's very convenient because it means that magnetic fields, which you can think of as being sort of made from virtual photons, but the main point is magnetic fields affect both particles and antiparticles, and there's no kind of annihilation. It's not like when the antiparticle comes in contact with a magnetic field that it annihilates with something. The antiparticle is affected by the magnetic field the same way. Well, it has the opposite charge, but so it'll deflect oppositely and things like that. But it can be affected the same way by magnetic field. So what you try to do is to contain the antimatter with sort of a magnetic bottle that keeps it keeps the thing away from any actual material. If you have a bunch of antiprotons and you let them hit, the metal side of your container, kaboom! There will be a big. There'll be a bunch. They'll annihilate. The antiprotons will annihilate with the protons, and they'll turn into, well, what actually happens when protons and antiprotons meet at low energy, they turn into a bunch of pions that decay into muons and neutrinos and photons and so on. There's a sort of cascade of particles that get produced, and those particles have lots of kinetic energy. They basically, what will happen is, just like in the Star Trek antimatter, engines or something, when you combine the matter with the antimatter, the mass of the matter and antimatter gets converted sort of into pure energy in a kind of E equals mc squared type way, and you'll end up with lots of kinetic energy. So that you avoid that by containing your antimatter so that it is contained with electric and magnetic fields, which don't distinguish between matter and antimatter, and so it's not like the antimatter is perfectly happy to interact with a magnetic field that's produced by matter type. So you use matter, electrons in wires and so on to produce your magnetic field, and that magnetic field happily interacts with antimatter and can be used to control where it is and contain it and so on. So that's basically how you contain antimatter. And people have these days made anti-atoms, for example, where you have an antiproton with a positron going around the antiproton. I think the largest there's certainly anti-deuterons that have been made. I'm not sure what the largest anti-nucleus that's been made is. I don't think that anybody's got as far as making anti-carbon or something like that with 12 protons and neutrons in its nucleus. I don't think that's been possible yet. But you can get sort of small numbers you can sort of have a little bottle of antiprotons that's maintained by electromagnetic fields. Let's see. Susie is asking, how would you think about photons as a 10-year-old? What's an easy explanation? Well, you can go back in history and ask what people thought light was. What is light? Is light a stream of little particles, or is light something different? You can ask that about anything. What is matter? So the first sort of fact that is sort of just a fact about the world, I don't think it's, I think it's something that it's hard to show that it's the case. It took until 100 years ago or so before people could show that it was the case, is that matter is made of atoms. That's just something you have to pretty much, you can do experiments, but I don't think there's an obvious, I'm trying to think, is there an everyday experiment in today's world that shows that matter is made of atoms? You're not allowed to go look at a quantum information lab or something. Then you get an easy way to know that matter is made of atoms. The way that people guess that matter is made of atoms is things like when there are chemical reactions, that there are integer ratios of the number of one kind of material and another kind of material, like that you have, H2O, and you have sort of twice as much hydrogen as oxygen and things. There's sort of an indirect deduction that happened in the 19th century about why atoms exist. But so I think the first statement to make is that things like matter, if you look at it on a small enough scale with a powerful enough microscope, like an atomic force microscope or whatever, you can see that matter is made of atoms. It's made of discrete things. So now the question is, what is light made of? Light is something different, and the question is, what is it made of? And is it something where you have a certain amount of light, and it was like with matter, if you have a small enough amount of matter, eventually you'll just have one atom, and then you have no atoms. Similarly with light, if you have light as it is ordinarily, and you make it dimmer and dimmer and dimmer and dimmer, if light is made of something discrete, then eventually you'll get to the point where there's just one of that thing it's made of, and eventually it'll go to zero things that it's made of. And so the sort of photons are the things that light, the discrete lumps of light. And in any, when you have when you're seeing things, or when you have a light bulb or something like that, you're getting trillions and trillions of photons produced by it. Now, it turns out that in our eyes, we are detecting, in the end, individual photons. In the end, there are molecules, rhodopsin, in the photoreceptors in our eyes, where an individual photon produces an individual electron that eventually produces an electric current that goes onto our optic nerve and causes us to have the sensation of light having fallen somewhere. We're not normally sensitive to individual photons. It takes a bunch of photons coming in together but our individual photoreceptors in our eyes are sensing single photons. If we were, I think it's said that the king crab, no, horseshoe crab. Well, what are they? The things that look much like trilobites, the deep ocean uh, crab-like things. They have very good eyes, and it's claimed that they can they're sensitive to probably down to individual photons, that they can see individual photons, so to speak. And it's kind of a funny thing. If you imagine being able to see individual photons, you'd start seeing your visual impression of things would be coming in little dots. You wouldn't, normally when we look at things, it's like, okay, we're just seeing the scene as it is. We're not seeing the scene be built up, pixel by pixel. So actually, yeah, here's perhaps a way in terms of the sort of the way of thinking about light as discrete things. It's a little bit of a different thing, but a way to kind of see that things could be discrete, even though you don't see that obviously, is just look at a computer screen. And a computer screen, you've got all these pictures on the computer screen, and they look like they're continuous. But if you look under a magnifying glass, you'll see the computer screen has little red, green, and blue dots on it, or bars on it. And it's kind of giving you the impression that there can be discrete lumps of light that give you the impression of something which is just a visual scene with gradations of color and so on. It's not the same phenomenon. Those individual pixels on the computer screen have zillions of photons coming from them, but it's at least some idea that it's not crazy to think that sort of the light that you get in your eyes is coming in discrete lumps, even though we have the impression that it's a kind of a continuous picture. Let's see. Well, there's a question from Yoloko about antimatter again. Sort of what is antimatter and why does it exist? I talked about what antimatter is. It's like you are reversing the charges of a particle, electron, proton, whatever else. Now the question is, why does it exist? Why is there an anti-version of all those things with the reversed charges? That's a tricky business. Let me try and explain it. So in fancy quantum field theory, there is this thing called charge conjugation. You can think of it as a mathematical operation. You apply the charge conjugation operation to something which represents a quantum field or a particle, and you get the anti thing from it. So it's kind of like saying, I've got the operation minus, and I've got a number like 2, and I apply minus to it, and I get -2. And so for every 2, there's a -2, and so on. Well, it turns out that for physical particles, there's a thing like that. It's called charge conjugation. And when you have a mathematical description of a particle, you can apply charge conjugation and you get the antiparticle. Now, a little bit fancier from a math point of view, when you represent the particle mathematically, you have, well, either its so-called wave function or its field operator. These are just mathematical constructs that represent things like particles. And the charge conjugation operation takes the complex conjugate of, let's say, the wave function or the field operator, or roughly the field operator. So that means if you know about complex numbers, there's I, the square root of -1. So you're taking I to -I. That's what taking the complex conjugate does. So mathematically, charge conjugation, the going from particle to antiparticle, works by this operation of taking the complex conjugate. Now, that's not a very physical thing to say. That's the mathematical description of what's going on. Now, why is it the case that there are that there are both the thing and its complex conjugate both exist? Well, the boy, this is a bit complicated. Okay, the roughly what the story will end up being that relativity implies that that must be the case, but that it's a bit of a shaggy story that goes from one to the other. So here's how it works. In quantum field theory, there's a thing called the CPT theorem. What does that say? So you have something, an atom, a bunch of particles, whatever, and you say what you might say, I've got a bunch of particles. I'm going to find the antiparticles of those particles. I'm going to just construct mathematically the thing representing the antiparticles. Another thing you can do is say, I've got this configuration of particles. I just want the mirror image of the positions of those particles. That's an operation called parity, P. It's actually really space inversion. You're taking a bunch of positions and you're kind of inverting them through the origin, let's say. But basically, it's like more or less a mirror reflection of things. Okay, so one question is, if you have a phenomenon that happens and then you find the mirror image phenomenon, do both phenomena happen in nature? So before 1956, people assumed that the way it was said, that parity is conserved. That is, that whenever there's something that can happen, where it can happen when things are in one orientation, it can also happen when they're in the mirror image orientation. Turns out in 1956, it was discovered experimentally that that's not the case. And in fact, this beta decay that I was mentioning earlier is the place where that was discovered. And the real clincher of the whole thing is that neutrinos operate, they kind of have they sort of have a spin direction, and they're always kind of left-handed relative to their motion. Their spin direction is oriented against the direction of motion. Antineutrinos, it's the other way around. That phenomenon breaks this mirror symmetry possibility. And so we know that in actuality, P parity there are processes in nature where the mirror image is not the same as the process itself. I mean, possibly, conceivably, the fact that all the molecules that biology uses are right-handed molecules, this operation goes from a right-handed molecule to a left-handed molecule. Possibly that fact about beta decay might be why in the early Earth, when life was first formed, that there was a slight preference for right-handed molecules over left-handed molecules, maybe. Or maybe it was just coincidence. But in any case, so parity not quite conserved. The other operation in this CPT combination is time reversal. And time reversal is you have something that happens and you say, well, what about the reverse of that? What about if we flip around the movie and we're running the video in reverse, so to speak? Can that also happen? Again, earlier on, people thought that time reversal was perfect in physics. In 1964, it was discovered that there isn't perfect time reversal invariance. It was discovered in a rather obscure case of the decay of the neutral kaon particle. And it's a slightly obscure thing, but basically that's a particularly sort of sensitive case, which sensitively depends on whether, well, roughly what happens is, gosh, this is a bit complicated, but roughly in a kaon, it's a type of particle. A kaon is a type of particle. It has a mass of about half the mass of a proton. It's a particle that decays in about 100 millionth of a second. There are particles called pions, which are famous because they are the particles that are exchanged between protons and neutrons in nuclei that bind the nuclei together. They're what mediate the strong nuclear force. Pions have a mass of about a tenth the mass of a proton, kaons are kind of a little bit like pions, but they're so-called strange particles. That means that, okay, so a pion, Okay, there are different kinds of quarks that make up particles like protons. Like a proton is roughly two up quarks and a down quark, plus a bunch of other fuzzy gluons and other such things. But it's roughly two up quarks and a down quark. A neutron is an up quark and two down quarks. So then a pion, a pi plus, there are three kinds of pions, pi plus, pi minus, and pi zero. A pi plus is an up quark and an anti-down quark. So in addition to the up quark and down quark, there also is a strange quark, and a kaon, like a K plus, is an up quark and an anti-strange quark. And the K0 is an anti-down quark and a strange quark. A K0 bar, the antiparticle of the K0, is did I say this the right way around? A K0 is a strange quark and an anti-down quark. A K0 bar is an anti-strange quark and a down quark. So in any case, pretty subtle effect that now this is complicated. It requires, okay, so in a beam of kaons, K0s, they actually will, some of the time, they will transfer to being K0 bars. That's a sort of quantum mechanics phenomenon. It has to do with the fact that the combination, well, the fancy way to say it, the quantum eigenstates, the sort of the stable states that you make from kaons and antikaons are combinations. There's a stable state called the K long, K0 long, another one called the K0 short. Those are two states that are sort of the kind of independent states. But if you have a beam of K0s, it will sort of oscillate and it will appear to be K0 bars some of the time. Okay, so the subtle effect is if you look at those oscillations from K0 to K0 bar and you look at them kind of going forwards in time as we experience time, then they will have one form. If you were to reverse them, they would have a different form. So if you're wondering, is time going backwards for you? If you have a beam of K0s, you can look at its oscillations and you can say, no, yes, I'm okay. Time is going forwards for me. If you look at the oscillations and it's different, then time will be going backwards. That's a signal of time going backwards. So, okay. So of these things, CPT, all three of them actually. So along with parity violation, you also get charge conjugation violation. It's a little bit tricky to explain. It doesn't really matter. The main point is that you have these different features of, but what seems to be the case is that the combination of charge conjugation, parity, and time reversal, that always leaves you with something which can happen the same way. So in other words, if you take some configuration of particles and you say, I'm going to look at the version of this where every particle has been turned into an antiparticle, space has been inverted, time has been reversed, the result of that will always be a thing that happens with the same probability, that has the same characteristics as the original thing. And so, for example, if the masses of particles appear to be something where you get from the mass of, roughly the fact that particle masses and antiparticle masses are the same is a consequence of this. But roughly what happens is this, gosh, this is a little complicated. As I said, these different forms of explanations for things have different levels. This one is a kind of advanced graduate school quantum field theory level story. So it's a little bit more complicated than some of the other things I've talked about. But in any case, so roughly we're trying to explain why antiparticles exist. And so what I'm explaining is that there is this CPT operation that you can apply to anything and you'll get a thing that's also a valid thing that could happen in the universe, so to speak. And the way that you kind of prove that that's the case within the mathematical formalism of quantum field theory is it turns out that in relativity theory, you say one of the kind of concepts of relativity is that you never know absolutely how fast you're going. You're always you have a certain reference frame where you say, I'm at rest. And oh, that rocket is going really fast. But the rocket could say, well, I'm at rest and you're just going really fast relative to me. And the claim is that it doesn't matter absolutely how fast you're going, things will always look the same to you. That's the concept of relativistic invariance. And the thing is that in it is a bit tricky because in order to maintain relativistic invariance and knowing that the speed of light looks the same regardless of how fast you're going, those two things together imply that space and time have certain sort of combined characteristics. So when you're going very fast, lengths are foreshortened, times are slowed down, and so on. And that's a feature of relativity that you have these transformations about space and time when you are when things to make things really look the same to you when you're going at different speeds and have the speed of light always be the same, you have to sort of mess around with space and time. Okay, so the thing that happens is if you if you believe in relativistic invariance, you believe that things will always look the same to you regardless of what speed you're going at. It turns out that extending that idea of what speed you're going at, even beyond the speed of light, basically, you end up making a transformation which corresponds to the CPT transformation. So it's as if assume everything works relativistic invariance. Everything sort of looks the same at any speed, and then say let's extend that a bit further. And the mathematics of quantum field theory says you should be able to extend that a bit further. When you extend that further, what happens is that actually you extend it to the point where time flips around and so on. When that happens, you're applying the CPT transformation but it's essentially a consequence of Lorentz invariance, relativistic invariance, that things have to be invariant under the CPT transformation. The result of that is when you untangle that, it means that there has to be, that things have to allow this charge conjugation operation, which means that you have to be able to have both particles and antiparticles. That was a very elaborate explanation. I'm sorry, that's complicated. But within the framework of quantum field theory, at least, it is sort of necessary for the mathematical integrity of quantum field theory that there exist antiparticles as well as particles. Now, you could say, well, maybe quantum field theory is nonsense. It doesn't seem to be. And so then you're sort of out of that box. But mostly that's how that works. That there's sort of necessarily, just as you can think of reversing time, inverting space, you can also think of making particle-antiparticle transformations, and all of those are possible. So I suppose one way to say it is it's as possible theoretically to go from a particle to an antiparticle as it is to sort of flip yourself around in space. And that's why antiparticles sort of have to exist. Question of why we end up with well, I can explain a little bit actually of the matter-antimatter asymmetry in the universe. So it's a pretty subtle effect, and we don't really know why it happens. But roughly, it is a consequence of that same phenomenon that was discovered in 1964 of the violation of time reversal invariance, which, because CPT together is left invariant, if time reversal makes a change, then CP also has to make a change. The combination of charge conjugation and parity also sort of makes a change. Well, okay, if it is the case that there are CP violating processes in the early universe, then it turns out that the expansion of the universe combined with that can lead to this asymmetry between particles, matter and antimatter. In particular, well, here's roughly how it works. Particles, antiparticles, if you have, for example, a neutron, I said it has a lifetime of about 15 minutes. An antineutron also has a lifetime of about 15 minutes. It is a consequence of the CPT invariance idea that the complete lifetimes of particles must be the same as the lifetimes of their antiparticles. But if a particle can decay into several different kinds of things. So famously, the K0, the aforementioned K0, can decay into, well, it can decay into either 3 pions or 2 pions, different charges of pions, and so on. Each of those possible decay modes has a certain probability. If you've just got a K0 sitting there, then in, what is it, 10 to the minus 10 seconds, so a 10,000 millionth of a second, the kaon will sort of explode into either 2 or 3 pions, roughly. Actually, it can also go to a muon and a neutrino, but that's a different story. So in any case, it turns into, so the rate at which it goes to 2 pions, the rate at which it goes to 3 pions, those are, there's a certain probability that it goes to each one of those. Well, it turns out that even though the total lifetime, the total probability that it decays at all is the same between a K0 and an anti-K0, the rate at which it decays to a particular final state, like 2 pions versus 3 pions, can be different between the particle and the antiparticle. It's a fairly subtle effect. That's a consequence. So that difference violates the CP invariance. Also can be thought of as violating time reversal invariance. And so that small, you can have a difference between those things. So if you believe that there were particles that existed in the early universe, that very massive particles that actually also, oh boy, more complexity here. Well, let's just say if there were particles that have maybe masses of, let's see, 1,000 trillion times the mass of a proton, there's some reason to believe such particles exist, although we haven't observed them because we don't have accelerators powerful enough to produce such particles, but they would have existed in the sufficiently early universe when the universe was hot enough to just produce such particle-antiparticle pairs. Those particles probably had decay processes which have this difference between one decay mode and another decay mode. And that tiny difference between those decay modes can lead to producing more matter than antimatter, and hence our existence, so to speak. That, as I say, it's just 1 part in 100 million is the difference between the amount of matter and antimatter that was produced in the very early universe. And when I say early universe, this is very early time. So this is, oh gosh, before 1 trillionth of a second after the beginning of the universe, that these kinds of things have to happen. Let's see. Oh boy, I have to go very soon here. Brianna is asking about matter and antimatter and picking things at random. I think, yeah, well, I tried to give an explanation of that. Let's see. Okay, my last thing for today. Lpop says, are we unintentionally leaving behind a time capsule with light waves? Will scientists of the future be able to look back in time through light? The big problem with light is it always goes at the speed of light. So we produce lots of light, radio waves. They're just going out into the universe. And they just, it's not like we get to contain them. I mean, if we put, if we had mirrors, perfect mirrors, and we could bounce this light back and forth, I suppose we could contain it. But generally, we're just radiating radio energy, light, and so on out into the universe. And that's and so if you could go and look at all the light that came from the Earth, or even all the radio waves, but all the light that came from the Earth, and you were collecting it somewhere, you could say, yeah, I can see what it was like on Earth back at that time, so to speak. I mean, in other words, if you were somewhere halfway, across the, well, even if you were 1,000 light years away from the Earth, and those photons that are mostly photons, the universe is pretty transparent. So photons, even of light, I mean, we know it's pretty transparent because we can see stars from a long way away. So photons coming from us, they'll just trundle through space, going 1,000 light years. If you collect them 1,000 light years away from us, there won't be, they'll be the density of photons that you'll get is rather low because there's a lot of different directions you can go 1,000 light years away from here. But if you could collect them all, then yes, you could determine what things were like when those photons were first emitted in a sense 1,000 years earlier. Although even the definition of what you mean by 1,000 years earlier is hard to make because it's kind of like there's no sense in which a clock. The only way you know what time it is by being able to. You could say, well, I'm watching this clock, but I'm seeing that clock delayed by 1,000 years because that's the time it took light to reach me. I think I have to run off to something quite different. But boy, that got a bit deep into graduate school physics. I hope I'd actually be interested to know whether people were able to follow that, whether I succeeded in explaining that clearly enough. But it was a little challenging there. But anyway, thanks for joining me and look forward to talking with you another time. Bye for now.